Hi, today we'll be talking about post-quantum UPK schemes using supersingular isogenies. Okay, so let's start with the motivation behind our paper. Some online conversations can occur during months, if not years. For those types of conversations, we need a security protocol that is at the same time forward secure and post-compromise secure. Uh, Key-Updatable public key encryption, also known as UPK schemes, fulfill that role for those type of messages. However, currently, every single UPK scheme relies on discrete logarithm, with the obvious problem that D-log is not quantum secure. Now, let's talk about our results. We performed the first assessment on the viability of quantum secure UPK schemes. We also present a series of steps demonstrating that while SIDH can in theory be used for symmetric UPA constructions, because of current mathematical limitations, a viable construction is still hindered. On the other hand, we present a valid CSIDH based UPK scheme that can be used with existing parameter sets. So, what is a UPK scheme? It is a tuple of six different algorithms: a key generation algorithm, an encryption algorithm, a decryption algorithm, an algorithm to generate the update values, an algorithm to use those update values to update the private key, and an algorithm to do the same thing with the public key. From UPK schemes, we require five properties. The first one, obviously, is that it is correct. The second one is that it is forward secure. By that we mean that obtaining an updated key should not give any information on the original key. The third property is that it is post-compromise secure. By that we mean that obtaining the original key should not give information on the updated key. The fourth property is asynchronicity. This means that any party involved can update the keys. And the final one is key indistinguishability. This means that if we give someone the original key and the updated key, one cannot tell which is the updated key. Uh, this fifth property is not always necessary, but we will use it for a theorem. We separate UPK schemes into two categories: symmetric and asymmetric. The symmetric UPK scheme works as follows. The keygen algorithm is as usual. It accepts a security parameter lambda and outputs the public key and the secret key. The encrypt algorithm is also as usual. It uses the public key to encrypt the message and outputs a ciphertext. The decrypt algorithm works as usual also. It uses the secret key and the ciphertext to generate the message. The gen update accepts a parameter lambda and generates a randomly generated update value mu. And update private uses that mu to update that secret key. And update public uses that mu to update the public key. The asymmetric UPK scheme is very similar to the symmetric one, with one difference. The keygen, encrypt, and decrypt algorithms are exactly the same as in the previous case. However, the gen update algorithm uses the same parameter lambda to generate two different update values. One that will be used for the secret key update, and one that will be used for the public key update. A quick note on asymmetric UPK schemes. Because the private and public keys are updated with distinct values, we require a holomorphic structure between the public key domain and the secret key domain. However, no such structure exists for either SIDH or CSIDH. Because of that, we will concentrate on symmetric UPK schemes for the rest of the presentation. We want our UPK schemes to be what we call IND-CPAU. This means indistinguishable under chosen plaintext attack with updatability. This is a modification on the classic IND-CPA definition that has the following game. We have our adversary and our challenger. The challenger starts by generating the secret and public key and presents the public key to the adversary. and then the adversary can present a message, and for that message, the challenger must present the encryption. The adversary can repeat this step until they are satisfied. When they are satisfied, they present a final message M prime, and then the challenger can either show the encryption of that final message or just a random text. And the adversary wins if they can correctly guess the final choice of the challenger. In the IND CPAU variant of the game, the adversary is given more options on what to do in the intermediary phase here. As always, they can present the message to get the encryption. However, they can also present an update value to force the challenger to update their keys with this update value. They can also just demand an update, which forces the challenger to update with a random value. And finally, they can choose a key to corrupt, which forces the challenger to present the chosen secret key. And then remark that those 4 intermediary steps can be done in any order, and the adversary is also given the possibility on doing, for example, presenting a message, demanding an update, and then just going back to present another message. Also, what changes is the endgame here. Before, the adversary just had to present a fresh message. However, this time they must present a fresh pair of one public key and one message that has not been encrypted with that public key yet, for any non-corrupted secret key associated with that public key, and the challenger must either encrypt the message with that public key or just give a random text. As always, the adversary wins if they can guess the final choice of the challengers. Also in INDCPAU, we offer the adversary an additional way to win. That is, if they decide to corrupt the key and then find a chain of updates that lead to that key, they also win. This is because we want to represent post-compromise security. The first UPK variant that we will try today is on SIDH. Recall how SIDH works. We have an initial curve E, we have 2 parties Alice and Bob, and we have 2 prime numbers A and B. The secret key of Alice is an isogeny phi A, whose kernel lies in the A torsion of E that goes from E to EA, and similarly for Bob, it is an isogeny phi B that goes from E to EB, whose kernel lies in the B torsion of E. The public key of Alice is the curve EA and the auxiliary point of the B torsion on E. And for Bob, it is the curve EB and the auxiliary point on the A torsion with the isogeny phi B. And also the shared secret at the end is the final curve EAB that commutes this diagram. The naive way to update Alice's secret key in SIDH, let's say if the original secret key was phi A1, would be to add another isogeny phi A2 from EA1 to EA2, and then have that Alice's new secret key is phi A2 phi A1. However, this is not forward secure. The reason for that is that if someone can get phi A2 phi A1, they could use this information to obtain phi A1. To deal with this issue, we can use the KLPT star algorithm, which is a modification of the original algorithm by Kohallotiepati and Tignol. This improvement was made by the authors of SkiSign. How it works is that given an elliptic curve E0 and E1, also given their endomorphism rings, it returns a left ideal of the endomorphism ring of E0 that is also a right ideal of the endomorphism ring of E1. This can then be converted into an isogeny from E0 to E1. The important thing here is that this new isogeny only dependent on the curves and their endomorphism ring. More importantly, it did not depend on any other isogeny. This means that KLPT star can be used to find another isogeny between the same curves that is completely independent from the original one. Hence, let's use KLPT star for our SIDH UPK scheme. We know the original curve E and we know the endomorphism ring on the original curve E. We also know an isogeny phi A2 phi A1 from E to EA2. We can then use this information to evaluate the endomorphism ring of EA2. Now that we know both endomorphism rings, we can use KLPT star to get a new isogeny phi mu from E to EA2. We can then simply replace the old isogeny by the new isogeny to obtain a new SIDH exchange. However, this method has two issues. The first one is that this does not respect asynchronicity. This is because our method required the knowledge of the old isogeny, which was Alice's secret key, so only Alice can apply KLPT star. For now, this issue has no known solution. Also, we have another issue is that after multiple updates, the degree of phi mu can get too large. By that we mean that usually in an SIDH exchange, we use the kernel of the isogeny to define the isogeny, but if the degree of that isogeny is too large, we cannot do that. This second issue we can solve for now. How we do that is simple. We take our original isogeny phi mu and we separate it into a chain of smaller isogenies from phi A1 up to phi AK. And then what we can do is do the SIDH exchange on every single rectangle until we get the final elliptic curve EAKB, which will be the shared secret. However, Alice now requires the auxiliary point on every single intermediate curve in order to continue with the SIDH exchange. On the other hand, Bob cannot simply give both points because giving those 2 points would also just give the intermediate secrets. So how we deal with that? And we can remark that when we apply phi A to the A torsion of the previous curve, we get a subgroup of order A. This means that using linear algebra, if Alice knows the auxiliary points on the previous curve, Alice can get the auxiliary point on the image of that curve. So this means that Alice only needs one additional auxiliary point from Bob, and telling which auxiliary point she needs only gives one bit of information on her isogeny. In summary, our SIDH UPK works as follows. The keygen algorithm generates as a private key a chain of isogenies phi A1 up to phi AK, and as a public key it generates the auxiliary point of each of those isogenies, as well as the additional point that Alice will require for the complete SIDH exchange. For the encryption algorithm, we simply compute the final curve EAKB and use that shared secret for our private key scheme. The same thing happens for the decryption algorithm. For the gen update algorithm, we simply compute a new isogeny from Alice's final curve EAK to a new curve EAK plus 1. For the update public that anyone can do, we simply add phi AK and the auxiliary point of phi AK and the additional required point of phi AK to the chain. However, the update private that only Alice can apply uses KLPT star on this new final chain and repeats the keygen algorithm. When it comes to the 5 properties that we wanted a UPK scheme to respect, this SIDH scheme has the correctness property. It also has both the forward secrecy and the cross-compromise security properties once KLPT star has been applied. However, since KLPT star needs to be applied, we do not have asynchronicity. Also, for now, we do not have key indistinguishability because the length of the chain gives information on the number of updates. We now turn to our CSIDH UPK scheme. Recall that in CSIDH, the secret key is a vector of integers e1 up to el, with each component being in absolute value smaller or equal than a constant b. This is for the sake of fast calculations, and that vector represents the product of the canonical generators for our public key. The naive update that we can do in CSIDH would be to simply generate a new vector with from F1 to FL and have that the new public key is just the product of the generators represented by the old vector and the new vector, and the secret key would be the sum of the two vectors. However, this naive approach comes with two major issues. The first one is that finding the updated secret key gives information on the original. This will imply that we do not have forward secrecy. This is because the possible updated keys are always centered around the original secret key. For example, if we found out that the updated key had one component equal to 2b, this would guarantee that the original key had a component equal to b. Also, after multiple updates, the keys become much too large for any reasonable computation. There is a simple solution to both our issues. This comes from an idea by the authors of Sci-Fish. For this to work, the group structure must be known. For example, in their implementation, they worked on CSIDH 512 because it had a cyclic group. Let's call it a cyclic group of order n. So instead of representing sk as a vector of integer, we can represent it as a group element. Because of this, both the issues of having keys becoming larger and larger and the issue of having the new keys being centered around the old keys disappear because of the cyclic property of finite groups. Also, the Sci-Fish paper describes how to go from one representation that was the old representation to this new representation using finite groups. In summary, our CSIDH UPK scheme works as follows. For the keygen algorithm, we simply sample an element from that group and use that element to generate our secret and private keys. The encryption and decryption algorithm work as usual for CSIDH. When it comes to the gen update algorithm, we simply take another element from that group, and for the update private algorithm, we simply add this new element to our old secret key. And for the update public algorithm, we apply the group action of that new element on the old public key in order to obtain the new public key. In our paper, we show that this CSIDH UPK scheme is IND-CPA-U if and only if the classic CSIDH scheme is IND-CPA. In brief, in our paper, we defined what are symmetric and asymmetric UPK schemes. We also defined this new security property that is IND-CPA-U. We showed that UPK schemes can be implemented to be quantum resistant because of our CSIDH variant, and that CSIDH variant works as long as the group structure is known. When it comes to the SIDH variant, while it is still hindered because of existing mathematical limitations, we show some steps toward a valid implementation. When it comes to possible advancements, the simplest one is probably in the SIDH variant. This is because as long as we find a way to limit the size of the keys, we could attain key indistinguishability. When it comes to the CSIDH case, we can always find better algorithms to evaluate the group structure. Some note on that final point. There are currently sub-exponential algorithms to evaluate the group structure. Also, since we are talking about post-quantum algorithms, we have to remark that once quantum computers are developed, only one of the parties requires to have a quantum computer for everybody involved to have a quantum secure scheme.